The objective of this video is to introduce poles and zeros of transfer functions. We're going to talk about the calculation, conditioning, classification, and identification of poles and zeros. The overarching goal here is that we're developing tools that will enable us to study the dynamic behavior of our power electronics converters so that we can design regulators to control them. We have to do this by starting from the basic circuit elements and working up to transfer functions, and then placing the transfer functions into canonical forms so that we can easily recognize the poles and zeros of the transfer function. So starting with the circuit that we ended with at the last video, on the left here, we'll derive the transfer function. And this is again just a simple voltage divider. So we can say that G1 is equal to V out over V in, which is equal to R over R plus SL. And we put this in the Laplace domain, and that brings along with it a lot of baggage, which you have gone over previously in your signals and systems class. We know that we can convert this transfer function into a frequency response transfer function by evaluating the transfer function at S equals J omega. So we can say that this is the calculation phase, and then what we want to do is we want to condition this to get it into a canonical form. The act of conditioning is to make every term of our transfer function start with the number 1. So the numerator starts with a 1, the denominator starts with a 1, and then we have something multiplied by s. In this case, we have s times L over R. The idea here is that we've gotten rid of all units. So there are no units on this term, there are no units on this term, and this is a normalized impedance, which effectively has no units. The canonical form that we want to put this into has a gain, in this case it's 1, multiplied by our numerator, and then divided by our denominator, where we're expressing the denominator as 1 plus s over omega 1, and omega 1 in our case is equal to R over L, which we can convert to a frequency by dividing by 2 pi. So this is the canonical form for a pole. This is a pole at frequency R by 2 pi L, or in radians per second of R by L. And I had commented just a second ago about how we can convert this to a frequency response transfer function by evaluating it at S equals J omega. So if we have it in this form, we can easily recognize that if we were hypothetically to pick a value for our pole, let's say that our pole frequency is equal to 1 kilohertz, we can see that when we're operating at a frequency much lower than 1 kilohertz, when omega is much less than 2 pi times 1 kilohertz, in that situation this term here is much less than 1, and so our transfer function becomes approximately equal to 1. It becomes approximately just a simple gain. On the other hand, when omega is much greater than 2 pi times 1 kilohertz, our transfer function can be reduced down by realizing that at this point this term is effectively negligible. So when omega is much greater than omega 1, this term dominates and the other term is negligible. So what is 1 plus J 1000? It's approximately equal to J 1000, which is in the Laplace form 1 over s, and that is an integrator. So we can see that depending on the frequency we're operating at, our transfer function looks very different or behaves very different. At very low frequencies, it's a simple gain. At very high frequencies, it's actually integrating our signal. And the reason that we want to put it into this canonical form is that it helps us to see this. It gives us physical meaning into the equation. And it generalizes it, so it wouldn't have to be describing a circuit. It could be describing any system. So in our case, we're describing the output to input relationship of our circuit that we've drawn here on the left side. And we know in this circuit that when we're operating at really low frequencies, our inductor simply appears as a short circuit. And this is confirmed from our transfer function. At really low frequencies, our circuit behaves as a simple unity gain circuit, that is, V out is equal to V in, which is what we expect if we have our inductor appearing as a short circuit. And we know that at really high frequencies, our inductor is going to appear as a larger and larger impedance, which means that our output voltage is going to drop. And we can see that right here as well. As we go to higher and higher frequencies, the term in our denominator grows significantly, and our output voltage drops. We can also notice that our output voltage is going to change phase because this is a complex transfer function. So as omega over omega 1 is larger and larger, the denominator becomes purely complex, and we see that our output voltage is actually going to lag our input voltage. This makes physical sense to us as well. We know that inductors are reactive elements, and that the current to the inductor is going to lag the voltage applied across it. And since the voltage on the output side is just equal to the current times the resistance, we would expect the output voltage to lag as well. So we can see that our physical understanding of the circuit is confirmed with the transfer function. And by writing it in this canonical form, we can quickly pick out where the important frequency is. We can see that that important frequency is 1 kilohertz. Below 1 kilohertz, our circuit behaves more and more like a gain, and above 1 kilohertz, our circuit behaves more and more like an integrator. So let's now construct a table of different canonical forms that we'll be dealing with in this class. We've talked about a pole, and this should be familiar to you from other classes. We'll now talk about zeros, as well as inverted poles and inverted zeros. And these are concepts I expect to be new to you. So at this point, we've talked about calculation of transfer functions and poles and zeros, of poles, and then conditioning the transfer function to get it into a canonical form. Let's now construct a table of canonical forms. So this is going to be the classification and identification portion. The first entry in here is going to be the simple pole that we already discussed. And we can describe this as being a left half plane pole, or a real pole, or a simple pole. If somebody tells you that there's a pole at a certain location and doesn't give you any more information, that is, they don't include the adjective like left half plane or real or simple, this is the kind of pole they mean. It's like asking somebody for a sheet of paper. You don't usually have to specify that it's a white sheet of paper because normally paper is white. But if you want a red or a gray sheet of paper, you probably have to say, please give me a gray sheet of paper. So if somebody tells you that there is a pole at 1 kilohertz, they mean it's a left half plane pole, a real pole, or a simple pole. If you are describing a right half plane pole, you simply invert or you simply reverse the sign here. So you see that this is a positive right now. A right half plane pole has a negative there. Next, we'll describe a zero. And a zero goes in the numerator. So it's the same transfer function, but now it is up top instead of down below. And similarly, this is a left half plane zero, a real zero, or a simple zero. Well, in the case of the pole, we notice that at low frequencies it looks like a simple gain, but at high frequencies it looks like an integrator. We can make the same kind of observations about a zero. At low frequencies, when S by omega 2 is small, this term dominates here, the 1 dominates, and it's a simple gain. But at high frequencies, when S by omega 2 is very large, this term dominates, and it looks like a derivative. If you look back at your tables of Laplace transforms, if you multiply by an S, you have a derivative operation. Next, we'll talk about a transfer function of this form. So while I expect that poles and zeros, the first two entries are familiar quantities to you, I think that this transfer function may be new. This is called a left half plane inverted pole. Inverted because the term appears as omega 3 over s. And so this can be functionally decomposed into a zero and a pole. However, it is useful to view it in this form for reasons that we'll be discussing in videos soon. And it's something that we're going to be using in this class to assist us with back of the envelope type of calculations, with hand calculations. So we can have a left half plane inverted pole. We can also have a left half plane inverted zero, or a right half plane inverted pole and a right half plane inverted zero. So the final thing to note here is that right half plane poles and inverted poles are unstable. Unstable, what does that mean? That means that if I have an unstable system and I excite it with some excitation, some actual excitation, it will produce an unbounded response. It will blow up. It means that the response might look, if this is a graph of V out over time, it will look like this. It'll go off to infinity. So I now want to discuss some examples with you. And in each example, I want you to condition the transfer function that I give you. That is, I want you to convert it to the canonical form. So suppose that I gave you this transfer function. Your job is to convert it to this form right here, where you calculate the gain and the pole location. So press pause now, do your calculation, and press play when you're ready to resume. So you should have calculated this transfer function right here, where we have a simple pole at approximately 20 millihertz and a gain of 1/2. So in this case, this transfer function at the low frequency range, that is far below 20 millihertz, looks like a simple gain of 0.5. But at the high frequency range, which in this circuit is above 20 millihertz, looks like an integrator. Next, I want you to condition the following transfer function into the same canonical form. Press pause and press play when you are ready to resume. You should have found the following transfer function with a pole at 42 over pi hertz. Finally, I want you to calculate the canonical form of this transfer function, which corresponds to a circuit. Press pause and press play when you're ready to resume. So your result should look like this. And what we're doing here is we're setting the stage for being able to say, hey, I want to have a transfer function which has a zero at the frequency given by f4. And I'm going to realize this with two resistors and an inductor. What should be the values of my resistance and my inductance in order to get a zero at the frequency f4? So this is now going back to the backwards problem, or the inverse problem. We're trying to build up a set of tools that allows us to specify a desired transfer function, which is going to be our controller, and then figure out the circuit components that are needed to make that transfer function within our circuit. So that is the task of an engineer, time and again, is to know our analysis tools, which brings us from circuit elements forward to a transfer function, but also to be able to invert the problem and go from a desired transfer function to our circuit elements.